Hello and welcome to The Explainer. Today we have a really ambitious and honestly incredibly exciting goal. We are going to completely open up the hood of large language models to see exactly how they work. And we're going to do it from the ground up without getting lost in a maze of academic jargon. So if you've ever found yourself wondering how these massive systems actually tick, well, you are absolutely in the right place. Let's dive in. Here is our quick roadmap for today. We'll start by defining large language models, then we'll look inside the transformer engine, explore tokens and massive pre-training, talk about teaching AI with human feedback, and finally, wrap things up with real-world applications and risks. All right, Section 1, Defining Large Language Models. Let's establish a really clear baseline here and cut through some of the buzzwords we hear every single day, like Gen AI and ChatGPT. Generative AI is this massive umbrella term. It covers systems that create anything from images and videos to synthetic audio. Large language models, or LLMs, are a highly specialized subset sitting right under that umbrella. So while all LLMs are a type of generative AI, not all generative AI systems are LLMs. By focusing strictly on LLMs today, we're zeroing in on the ultimate specialists. These are systems designed specifically for interpreting, processing, and generating human language. Moving right along to Section 2, Inside the Transformer Engine. To really understand how these language specialists work, we have to start at the foundational level, which is neural networks. At its core, a neural network is a machine learning model heavily inspired by the biological neurons in the human brain. The best way to think about it? Imagine the network's weights and biases as this giant, incredibly complex dashboard of dials and knobs. Let's say you're building an AI just to detect spam emails. When the system reads a word like prize or money, it turns specific dials up or down to decide exactly how strongly that word should influence its final decision. The whole thing is basically about mapping inputs to the correct outputs through layered computation. Okay, so how does it actually learn to set all those millions of dials correctly? It uses a continuous training loop. First up is the forward pass, where data flows right through the network to make a prediction. Next is the error calculation, basically asking, okay, how far off were we from the actual truth? Then comes the real magic step, backpropagation. This is where that error signal travels backward through the layers of the network. And finally, the weight update, where the system actually adjusts those dials to reduce the error for next time. When you repeat this iterative process billions of times, this engine learns some seriously meaningful patterns. Now, for a long time, language models were kind of stuck in the slow lane. They used what are called recurrent neural networks, or RNNs. These read text sequentially, strictly from left to right. As you can imagine, that is painfully slow, and honestly, they were pretty terrible at understanding long paragraphs. But in 2017, there was this massive, industry-altering breakthrough, the transformer architecture. Using a brilliant mechanism called self-attention, a transformer reads all the words in a sequence simultaneously. It can connect any two words instantly, no matter how far apart they are in the text. This made training lightning fast, deeply context-aware, and highly parallelizable. It was a total game changer. That brings us to Section 3, Tokens and Massive Pre-training. So we've got the engine, but what about the fuel? How do these systems actually digest the entire internet? Which brings up a really fascinating question. How does a purely math-based algorithm comprehend a word like apple? I mean, a computer doesn't have eyes or taste buds, right? It literally only knows numbers. Well, the answer lies in something called tokens. Before an LLM reads text, it breaks words down into smaller chunks. These are your tokens. These tokens are then encoded as vectors. Actually, to put that simply, vectors are just lists of numbers that plot the token into a massive multidimensional space. And here is the cool part. The closer two token vectors are in this mathematical space, the more related their underlying concepts are. So when an LLM is generating text, it's fundamentally playing a complex, high-speed game of finish the sentence. Some experts playfully call it spicy autocomplete. It is simply predicting the most mathematically plausible next token based on its vector mapping. And this approach has evolved at just a blistering pace. Let's trace the timeline of OpenAI's GPT models for some perspective. In 2018, GPT-1 launched with 117 million parameters, basically proving the foundational concept worked. Just a year later, GPT-2 scaled up to 1.5 billion parameters, and it demonstrated these stunning zero-shot abilities, meaning it could perform tasks it was never even explicitly trained for. By 2020, GPT-3 blew the roof off with massive scaling, turning into a full-blown commercial API platform. And then by 2023, GPT-4 introduced multimodal inputs. That meant the language model wasn't just doing text anymore, it could actually reason about images too. Let's jump to Section 4, Teaching AI with Human Feedback. Here is the thing. Scaling up the parameter size, that's really only half the battle. We have to ask, how do we take a raw, totally unpredictable text generator and turn it into a polite, helpful assistant? Remember, an LLM pre-trained on the open internet with zero guidance might output complete nonsense, extreme bias, or absolute horrors. It doesn't know right from wrong. It just wants to predict the next word, regardless of whether that word is helpful or totally harmful. To steer the model, developers rely on a process called RLHF, which stands for Reinforcement Learning from Human Feedback. First, in supervised fine-tuning, actual human labelers write out ideal responses to various prompts. Then, they train a separate reward model. They do this by having humans rank different AI outputs from best to worst. Finally, the main model is optimized using policy gradients. Through this, the model literally learns to consistently produce those higher-ranked, human-approved answers. You can think of RLHF as essentially the steering wheel that aligns the AI's behavior with human intentions and safety expectations. And that steering is getting more sophisticated every day. Newer models, like OpenAI's o1, utilize a brilliant technique called chain-of-thought reasoning. Instead of just blurting out the first obvious and potentially wrong response, the model is trained to break complex, multi-step logic problems down into their constituent parts. It actually takes time to think and assess a problem step by step before it predicts the final text. This vastly improves its performance, especially in tricky math and logic problems. And finally, Section 5, Real-World Applications and Risks. Now let's bring this right back to your world and examine how these aligned Taylor models are driving actual industry changes. We're going to look specifically at a highly complex sector, asset-based finance, or ABF. We're seeing three major LLM use cases emerge here. First up is sentiment analysis, having the AI read thousands of financial texts to instantly gauge market mood. Second is question answering, which allows users to query dense financial documents and get plain language answers back. And third is named entity recognition, which is pinning down and categorizing companies, commodities, and complex financial instruments automatically. What researchers are consistently finding is that fine-tuning these models on domain-specific datasets yields vastly superior results compared to just using an out-of-the-box generic model. A perfect real-world example of this is Cardo AI. They use customized LLMs to automatically categorize small and medium-sized businesses into specific economic sectors, which is a massive help for lending institutions that are often dealing with very limited data. They even use these models to extract human capital KPIs directly from unstructured text. By combining the raw processing power of a transformer model with the deep expertise of human financial analysts who design the highly specific prompts, Cardo AI makes these complex lending tasks incredibly accurate. But let's pump the brakes for a second, because I want to be very clear here. LLMs are not infallible magic oracles. There are major limitations we have to talk about. We absolutely have to watch out for hallucinations, which is when the model confidently, completely fabricates information. There's also the ever-present risk of bias that was encoded directly from the massive training data. And in dynamic markets like finance, LLMs suffer from high temporal sensitivity. They don't instantly know breaking news unless they are specifically updated. Plus, feeding highly sensitive client data into an external LLM poses massive data privacy and regulatory compliance challenges. As a recent report from Cardo AI put it so well, a robust risk mitigation strategy becomes essential to leverage AI's potential while mitigating its inherent risks. The future of using LLMs in high-stakes industries relies entirely on precision, strict human oversight, and carefully curated training data. It is absolutely not about blind trust in an algorithm. It's about treating the AI as a wildly powerful, yet still fallible tool. Which leaves us with this final thought to chew on. AI models are steadily shrinking in cost and size, yet they are growing rapidly in reasoning power. We are moving away from simple chatbots into an era of tailored, agentic AI that can actually take actions for you. So as these systems become deeply integrated collaborators in your daily workflow, how will you adapt? Thank you so much for joining me in this explainer. I really hope this deep dive helped to mystify large language models for you, and I can't wait to explore more fascinating topics with you next time.